Okay, so we are looking at ET43, 17th of November 2012, Electrician's Theory exam. We're going to start with question 4 because it's the first question. Has maths or pictures, just going through the maths questions at this stage. So first one they want us to do is figure B shows an existing motor control circuit here. Figure A is a new remote start stop. So that's how figure A, remote start stop, and local stop station. Connect the new remote start stop station and the local stop station to the existing motor control circuit by removing one or more conductor from the existing motor control circuit. Show the removed conductor like this. So we're just going to put X's through it. Use 3 conductors. So it's going to be 3 conductor remote start stop station to connect the new remote start stop station and the local stop station to the existing motor control circuit. So stops need to be put in series. So what we have to do is bring that one down. It goes to the start of that stop. Then we actually have to delete this wire here. And we need a new wire to come along and come down to there because the starts are done in parallel. That one can then go to there. So we've got that start. Oh, I should have read this. This is a remote stop station. Oops. Helps if you read 3 wire but 2 local stop remote stop. So bad rereading. So that one is not there either. It comes from the middle in here. That one. B, 3-phase induction motor is controlled by a star delta starter. State what would occur if the main contactor engaged, but the star contactor did not engage, and the timer eventually engaged the delta contactor. So what would happen is when you first turn it on, the main contactor would close, the star would not close, therefore it would be open circuit, the motor wouldn't work. Once the timer goes in, if the main contactor is in and the delta contactor closes, that will just direct online it in a delta. Now, on to the next page, which is the maths, which is why we're actually doing this question. So, we have a 3-phase induction motor is connected to the supply. The motor technical data is supply voltage 400 volts, frequency 50 hertz. That's probably irrelevant. Efficiency 84%, fully loaded. Input power 9.52 kilowatts, line current 16.96 amps. Calculate the output power of the motor. So we've been given the input power. So our formula for efficiency is EFF equals output over input times 100. So we now fill in our values. We've got our efficiency is 0.84% because I put it in times 100 equals so 84% equal 84 equals our output, which is unknown, over our input, which is our 9.52 times by 100. So first I'm just going to divide this side by 100, which means I have to divide this side by 100. So I actually end up with 0.84 equals output over 9.52. If you don't want to do that step and just write in 0.84 instead of 84%, feel free to. That's what I normally do, but just in case someone wanted a reminder on that part. So now we rearrange this so that it's output equals. So what we do is we are currently dividing by 9.52, bad handwriting, sorry, 52 not. So we need to multiply by 9.52, and then we have to do that on the other side, 9.52 times. These 9.52 cancel, so we end up with output equals 9.52 times by 0.84 equals, if we put that in a calculator, 9.52 times by 0.84 and we get 7.9968. So um, rounding this to two decimal places anyway, equals 8 kilowatts. And if we go to our answer sheet, wherever that is, our answer sheet says 9.52 times 0.84 equals 8 kilowatts. Now, on to the next question. Calculate the power factor of the motor. So, our formula for this, power equals root 3 times I line times V line times P dot F. Because this is input powered, multiplied input power multiplied by power factor to get real power, output power. So in this case, we know our input power, which is 9.52 equals, and then we've got root 3 times I line, which is our 16.96, times by our V line, which is 400 volts, times by our P dot F. Now we need to rearrange this, so it's P dot F equals. So divide both sides, root 3 times 16.96 times 400. And then we do the same on this side, root 3 times 16.96 times 400. They cancel, they cancel, they cancel. So we now have P dot F equals 9.52 over root 3 times 16.96 times 400 equals. So we have our root 3 times 16.96 times 400 equals, and then it's not 9.52, it's actually, change that to watts, 9520 divided by answer, and we get 0.81. Because this value was going to give us it in watts, and that was kilowatts. So our power factor is 0.81. Which, if we look at the answer sheet, what's it saying? 9520 divided by root 3 times 400 times 6.81. Same again. Next question we are looking at is calculate the input kVA of the motor. So, input kVA, this is where we get the input power, which was our page. Now, input power was 9.52, and then we divide that by our power factor. So, divide by 0.81 equals kVA. So kVA equals, we go 2 divided by 0.81, and we end up with 11.75 kVA, which that is what we have as our final answer, the 11.75. Okay, so we are doing Et43, 17th of November 2012, and we are working on question 7. So in question 7, new factory has been constructed that incorporates some imported machinery that operates at a voltage other than standard low voltage. A dedicated supply is required for this machinery. 150 kVA 3-phase delta star transformer will be used. The characteristics of the transformer are turns ratio of 43.3 to 1, primary voltage of 11 kV. So let's start by drawing this. So it is a 150 kVA. Write out the full value, so 150,000 VA. it is delta star. So we draw our delta and we draw our star. Now we know it is 43.3 to 1, and we know the primary is 11,000. Now we get our primary and we divide it by our 43.3. Because it's 2, 1, we don't have to multiply it by anything. If it was 2, we would multiply it by 2. In this case, it's multiplied by 1, so it's the same value. We get our voltage here of 254.04. So just leave it as 254 for this one. Then we're just going to go to 0 decimal places. And then to work out our voltage here, times by square root of 3, and we get 440 volts. Now, that is generally the types of things they will ask you to do in almost every exam. So I always start by that kind. It's just write down your voltages. It's probably going to ask us for current shortly. So calculate the second phase voltage. We now know that that is our 254 volts, and our calculation for that is V secondary, V phase secondary equals 11,000 volts over 43.3 volts terms. So terms and then volts. And then we would multiply that by the terms on this side. So one term, if it was a different ratio. Next, thereafter, the secondary line voltage. So for that one, it is simply 254 times by the square root of 3, which equals 440 volts. So that's our answer to question 2. We come over thereafter the primary line current. So for this one, we go VA equals, and because this is 3-phase, root 3 times I line times V line. Now we want to rearrange this so that it's I line equals. So we divide both sides by root 3 times V line, and then this side root 3 times V line. They cancel out, they cancel out. So I end up with I line equals VA over root 3 times, and then our V line, because this is our primary line current, is 11,000, which gives us VA equals 150,000 standard across the whole transformer. So 11,000 times root 3, and then 150,000 divided by answer, and we get 7.87 amps. Because the third digit is a 2, we round down. And if we look at our formula sheet, we can see 254 for the first voltage, 400 for the second voltage, and then 7.87 amps, which matches us so far. Now thereafter the maximum secondary line current. Now we do exactly the same formula. The only thing that changes is instead of being 11,000, it's going to be 440. So I line secondary equals 150,000 over root 3 times 400 equals. So we go 400 times by square root of 3. Just putting it in reverse because it's faster on the calculator. Then 50,000 divided by answer, and we get 216.50, 51 because it's a 6, 51 amps. I used 400, not 440. That's my bad. So 440 times by square root of 3 equals 150,000 100,000 divided by answer. Make sure you use the voltage from your actual question, not just habits of always using 400. So it actually equals 196.82 amps. And if we check the answer sheet, it actually says 196.83 amps. So curious where they get that from. Might be if I change that 440 to more accurate, so 11,000 divided, because we did round in this question, divided by the 43.3. It's giving us our voltage there. Then we times that by the square root of 3 to get our line voltage. And then we times that by the square root of 3 again, get 150,000 divided by our answer, and we get 196.81. So they're actually rounded the wrong way. Good to know. And I believe that's the end of that question. State the form of cooling that will be used for the 150 kVA transformer. It'll probably be air cooled or oil cooled or forced air cooled. Take your pick, natural air convection, just pick one that is suitable for a transformer of that size.